Okay, this is lecture number 7, motion of robots and differentiation. So now it's a good stuff. And part 1. Okay, it's here. So let's start from Mark 5 as an example by Dr. Furuta. And he is my boss right now. Used to be my student. I guess I've been telling them that many times. But anyway, if you look at the motion of Mach 5, only part of it working. And we had Dr. Yamato's EOM, equation of motion, here, equation of motion. And that's what's this. I showed you this in the first lecture. And where derivatives here and second derivatives and so forth. So when you're talking about the motion of the robot, you need derivatives and second derivatives, namely accelerations. All right, so therefore, to describe the equation, you need that, meaning that those are important, fundamentally important tools for us. So let's get used to use those tools. That's what we want to do today. Well, differentiation and speed. We discussed about the speed and differentiation. The axiom number 1, right? Differentiation is speed. So let's talk about differentiation, derivative, whichever you like. First of all, average speed we talked about, which is like from t1, position x1 at time t2, position x2, then that's the time interval, and this is the amount of change. So that ratio is the average speed, and that is okay for from here to there, how long they take, what was the average speed. But as you know, you have to control the motor speed all the time. So therefore, for us, what you needed is instantaneous speed. Differentiation. So that's instantaneous speed limit, and we write that one down as dx over dt. So you're talking about instantaneous speed. You have to specify where. Say like at t3 here, at this point here, you have certain speed, and at the same time, you know that this one here is a slope of that curve at that particular point. Okay. So the catch is how to compute this limit. You have to compute this limit to come up with instantaneous speed. Okay. To do that, let me just clarify some of the terminologies. Well, difference, I don't think you have any problem. Difference is just, take the difference, okay? And the evaluation, I used this one already, but this is f of x evaluated at x equal a, so that's f of a. Derivative, dx dt, t function. When I want to stress the fact that this is a function, I put the variable in the parentheses afterwards. And then differentiation is this one here. This is an operation, taking the limit of this one here. So what I wanted to stress here is that differentiation is an operation, and as a result, we get the derivative. Okay. So derivative of slope, as I said, at t is equal to tau, say, looks like this one here. At this point here, that's the slope. So you can find the slope. Well, that's reasonable, isn't it? If the speed is fast, it increases very fast, right? That's what it is. Now, because we have to take the limit here, there are two concepts we have to introduce. One of them is divergence. Limit goes to either plus infinity or minus infinity, because we are going to take the limit of the bottom denominator 0. So if you divide something by 0, It can go up to plus infinity or minus infinity. That's divergence. And the other way around is that the converges. This limit goes to a single value. That's what we want. Okay? All right. Then come back to take a look at why we don't want to take the limit. By looking at that, probably we can find an approach for this problem. Okay. Because obviously the bottom denominator becomes 0. We don't want to have that. What's the engineering approach? What do you think it is? It's very simple. If you have difficulty, get rid of that cause of trouble. And what is the trouble we have? That's delta t at the bottom. That's why we don't want to take the limit. So obvious approach is to get rid of delta t from the bottom. The question is, how? So we know the answer. When you have a quotient or division here, we know that we can cancel the common factor out of numerator and the denominator. Like you cancel both of them by 2, the kind of things. We have done cancellation, so why don't we try that again? Okay? It is not easy to see what's going on by just saying it, so let's use this example and see how it goes. All right, that's typical second order polynomial. So the derivative is like this one here. Okay, so let's compute each one of them. So you put t plus delta t into this polynomial here, so that's square plus 3 times that plus 5. And t, so that's this. So the next thing is to compute this one out. You get t squared blah 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 and that. And minus that. Okay. It's convenient, isn't it? All of those are in here. So all of them will cancel out, and the remaining terms all have delta t in it. And if you look at this way, it's so easy to cancel them out. So the cancellation and the result is this. Here, to let delta t goes to 0 is not problem at all, right? This one just disappears compared to 2t plus 3, so it's just 2t plus 3. All right. So therefore, the derivative of that particular polynomial was this one here, right? The derivative of that one happens to be that 2t plus 3. So like t squared becomes 2t, 3t becomes 3, and 5 disappears. Cancellation works. Cancellation works. Wow, great. So what do? Okay, let's do more example. How about this rational function, 1 over? Well, it was okay with polynomials, so next function would be rational functions. So let's try that. So once again, we compute this one here, and limit delta t goes to 0, 1 over delta t, this minus that. So you have rational functions subtraction. So what do you do next? Of course, you will compute the common denominator, right? So you multiply this to that, and you get this one here, and subtract it, then you have this. Only this one here. And that what's going to happen is that delta t and delta t, you can cancel them out. Like this one here, and cancellation. And then what it amounts to is that the delta t can be eliminated as delta t goes to 0. You have 2t plus 3, 2t plus 3, 2 of them, that's what you are coming up with. So, polynomials and rational functions seem okay. We can get rid of the delta t from top and bottom. How about trig functions, exponential functions, next ones. We'll move on to that, but before that, well, this limit operation, this was done mathematically, but we are engineers, right? So we should convince ourselves by using numbers, engineer's way. Okay. So what I am going to do is to compute this ratio for small delta x, both plus and minus. And then and compute the result. And for that, I use this simple example of x squared. For that, we know that the derivative is 2x, right? So what I do is compute this one here at x is equal to 1. So that's what I do. So x is equal to 1. So f1 plus delta x minus f1 over delta x. And let delta x goes down from 0.5 to 0.01, smaller number, decreasing, and also minus 0.5 to minus 0.01, increasing towards 0. Okay? And the derivative at x equal to 1, as I said, 2x differentiated, x squared differentiated as 2x, evaluated at x is equal to 1, that's 2. So this is the target. And see if we can get this number 2. Okay, this is the result. In this table, delta x comes down or go up. And you can compute x2 and fx2 and delta y and the ratio. As you can see, this one here comes down to close to 2, and the other side goes up to close to 2. If you plot it, you can see the situation much easier. Like this one here. So, target 2 here coincides. We get number 2, success. So, this is something you should remember. Whenever you have some theory and you want to convince yourself, use a simple example and use numbers and see if that works. Okay, quick break. Difference calculation for engineers. Well, we have computed the difference of a function, like this one here. When we compute the derivative, we have to compute the difference, this one here. Nothing wrong with this from a mathematical point of view. Let me call this A. But over here, delta t is assumed to be greater than 0. Well, we cannot do this in real world. Why? Why is that? Simple reason, very simple reason. Well, t plus delta t is a future. So for an engineer, whenever you see the variable t, you have to remember that this is time, t, okay? So f of t is the current value of f at t. T is current time, right now, okay? So therefore, t plus delta t is in the future, And you cannot measure the future value. You cannot tell what's going to happen in the future. So therefore, what's going to happen is that you cannot use this one here. Instead, how about this one here? This is in the past, so therefore, we can do that. We can measure the function or whatever it is and save it. That's all you have to do. So this one, you can do it. So therefore, instead of this one here, you use f of t minus delta t. Use this one here. Why this is okay? Because remember, delta t was defined to be t2 minus t1, wasn't it? So from this one here, you can write down t2 is equal to t1 plus delta t. And that's the one I've been using over there. But at the same time, you can write this equation in terms of t1, then you move this one here, so t2 minus delta t. That's what this one is. So either way, we're using exactly the same equation here. Okay. So whenever you do use computers to compute those differences and so forth, you should use this one here instead of that. All right. By the way, BTY stands for by the way. By the way, mathematicians, from mathematical point of view, if A is equal to B, then function is said to be differentiable at that particular point. Okay? So sometimes A and B could be different. Like, remember the RoboKick problem? P's and Q's you can choose, and depending on what kind of values you choose, your speed have jumped, right? That's the kind of situation can happen. Okay. So differentiation is a trig function. So the next function we have to deal with is a trig function, and that's this one here. So what's the next thing you want to do? Oh, no, first thing I should say. All right. If I were you, what I will do is this. We want to cancel this delta theta from bottom and top. That means that we want to make this one in a form of products, right? If you have product, then you can cancel. So what I do is I will use this identity, sine minus sine is equal to 2 times cosine times sine. This is a product. So if I use that into this one here, we got this one here and here, 2 theta plus delta theta. Here theta cancels out, so, and over 2 over 2. Theta plus delta theta over 2, sine delta theta over 2, and 2 here. So let's get this one into that expression, and this is what you got. You have a question, right? So where does delta theta over 2 come from? Well, actually it's from this one too. 2 is missing, right? So I divided top and bottom by 2. Get rid of 2 upstairs, and here delta theta divided by 2. Why do I want to do that? Because that's the one we have all over the places, delta theta over 2. So what we do is to name that to be delta theta over 2 to be delta phi or something. And when delta theta goes to 0, of course, delta phi goes to 0. So it's the same thing. And this is simpler. As I said, mathematicians are lazy. So don't want to write down this one again and again. Okay. So this is what you got. Now, if you look at those two, cosine theta plus delta phi goes to 0, that's perfectly okay. The reason for that is that, well, compared to theta, well, it will be gone, so it's okay. But how about this one here? Now, we cannot cancel delta phi, but sine delta phi goes to 0, as we all know. Sine goes to 0 as the angle goes to 0. So therefore, this is 0 over 0, so may converge to a final value. Okay, so let's look at sine theta and phi. Okay, I hope this stays here. All right, this is a unit circle, and we have a triangle. I mean, the arrow here and the angle phi, and all right, that's flickering a bit, right? Let's forget about that. Anyway, so in this diagram, this is phi, and instead of delta phi, well, I just don't want to write delta again and again. So instead of delta phi, I use just phi. And since this is a unit circle, that one is cosine phi, and this one is sine phi. And if you look at this one here, as 1, so that's tangent phi. And also, I use radian. Do you know the reason why? This is the reason. The length of an arc for an angle phi radian is phi. That's the definition of the radian. So here, this is the angle here. Therefore, what's going to happen is that this one here is going to be the length, going to be phi. All right. With that, so the length argues like this. We will do the mathematical tricks. Many of them, but this is the first one, which is sandwiching from both sides. We use that to find the limit of mathematical quantities quite often. So if you got used to it, you can use this technique as a tool when you do lots of those limiting operations. Okay, so how can you sandwich them? Okay, if you look at this figure, this is sine phi, and that's phi. So which one is bigger? Of course, this one is bigger, right? This is curved and doesn't come to b. And if you look at tangent phi, then which one is bigger? This is tangent phi and that. So the tangent phi is bigger than phi. So phi, arc length, is sandwiched between sine phi and tangent phi. All right. So what I do is that the sine phi, tangent phi, if you remember, is sine over cosine. So I can divide sine phi, then this side is 1, this side is 1 over cosine phi. And I got phi over sine phi. Looks like something which is close to what we want, but not quite, right? So what I do is to flip that, so that instead of that, I have 1 sine phi over phi and cosine phi. Note the reversal. I took 1 over. That's the reason why it's this. And also notice that this is positive. Sine, cosine, everything is positive. So therefore, this reversal takes place. All right. Now, take the limit. Using cosine phi goes to 1 as phi goes to 0. So if I take a limit of this one here, left-hand side doesn't change, right? It's just 1. And this one here, this one here, you have limit phi goes to 0, this, and right-hand side limit phi goes to 0 is equal to 1. Wow, sandwiching. 1 and 1. So this has to be greater than or equal to 1 and less than or equal to 1. So because of the sandwiching, this has to be 1. Wow, that's great. So if you put the delta, it's the same thing. Delta, delta, delta goes to 1. All right. So this one here, this part becomes 1. This part, delta phi goes away. So that's cosine theta. So we found out the derivative differentiate sine theta, you get cosine theta. Similarly, we can show that if you differentiate cosine theta, you get minus sine. And for tangent, we got 1 over cosine squared. Oh, this is interesting, isn't it? Okay. SP1, SP2, special problems. Try it. Then do compute this one here and that one. The interesting thing is that both of them can be shown using this one here, sine over delta phi. You can use this one here for both of them. Easy, so do it. Okay, that is the end of this lecture. Next time we will talk about the exponential function and few examples. Thank you.